In this video, we're going to explore carbohydrate reactions using a sample test question from Winter 2018 Test 4. We're supposed to start over here and draw L-talose. I think I have the information for D-talose handy. D-talose down here in the bottom corner. Bring it on over. Bring your eye level down here where I copied D-talose. We need L-talose, which is its mirror image. There it is. That's not D-talose. That's L-talose. L-talose needs to be up here so we can start the question. And we're going to use some enzymes to create a beta-3-aminopyranose. So before we even start, what's the beta-3-aminopyranose or beta-3-aminotallose look like? On carbon 3, we've drawn an amino in the place of the original hydroxyl. Now we have to make a pyranose. Here's the ring skeleton. Carbon 2, down OH, then down NH2 on 3, and down OH on carbon 4. Keeping in mind when we do the swinging around on an L sugar, the CH2OH here is going to swing to a downwards position after following all the instructions in our previous videos. And now the only thing to do is to put on the anomeric hydroxyl, because this is a hemiacetal ending with -ose. And when we're talking beta, it needs to be cis to this carbon here, which puts it in a downwards direction. And there is the beta-3-aminopyranose from L-3-aminotallose. Going to the alpha-2, oxygen has an ethyl group pyranose. The oxygen on carbon 2 is going to have an ethyl. Now we're working with this monosaccharide, and we're going to do a pyranose as well. This time we need the OH of the hemiacetal to be trans to the C because it's alpha. There's our O-ethyl, and we don't have an amino on this one, so we're finished with those two. Let's go straight downwards here, and we're supposed to draw the alpha pyranoside. That's a glycoside, meaning a full acetal. You need another alcohol to do that, and we are told the other alcohol is para-nitrophenol, and we're going to have to show all pi bonds. So let's look at para-nitrophenol for a second. Here's para-nitrophenol. Here is the generic alpha pyranoside of L-talose. The R group will be this phenol. This would be the blue O. So let's connect that. And this is alpha because it's trans to the C, and there's our para-nitrophenol as the nucleophile that replaced the oxygen of the hemiacetal. Acetals will not react under conditions such as the Tollens reaction, which we'll look at down here when it does happen. There will be no reaction for acetals, only hemiacetals, and the open fissure forms react. They're called reducing sugars when they're the open form or the fissure. And just changing the color of our font here so we can see it. No reaction. And that's dead end. All right, well, moving on to Tollens reagent here, also known as the silver mirror reaction because it generates silver. We're going to be taking our L-talose and reacting it, and it will oxidize only at the aldehyde. If we used a chromium reagent, it would oxidize every one of the alcohols. You'd get an OH here if the pH was low, but the pH is buffered to 10, so it's going to be a carboxylate. And you're going to have an anion there. what do we call an aldehyde that became a carboxylate in a carbohydrate? In chapter 26 we see this document, a carboxylic acid that's become a an aldose that became a carboxylic acid is an alderic acid. So if it was mannose, it became manneric acid, and we lose an H from the top. Oh, I don't think I read that right. This oxidized the bottom as well. The one that oxidizes only the top, that's what we just did, is an aldonic acid. So if mannose makes mannonate or mannonic acid depending on the pH, then talose is going to make talonate. And there you have it. So we've explored all the initial reactions that come directly from our talose. We're supposed to take our beta-3 aminopyranose here, and a couple things have to happen to make it into this. It's a hemiacetal, so it's in equilibrium with the open form over here. And the open form aldehyde seems to have become an acetal. We are experts at that by now. We're going to take this diol and make it into an acetal using a catalyst such as sulfuric acid, which we have here. I have to get rid of the paranitro. So this combination, using Dean-Stark trap to facilitate the dehydration step in the condensation reaction, we'll put the protecting group on the top. All that remains is to put an, if you think that's an ether, you would be making a mistake. That has to be a carbonyl. So this is a propanoyl group here. Chapter 18, we learned that's a derivative of carboxylic acids. We could use propionyl chloride. So there you have the amide. There's propionyl chloride. You could have used propanoic anhydride as well. And here's our product. And what's going to happen is we've protected our aldehyde against reduction. The alcohols are already reduced. The amide is going to be reduced to an amine using lithium aluminum hydride followed by sulfuric acid. Oh, and the sulfuric acid has water, which is a hint that it's going to undergo hydrolysis as well. So we're going to get our aldehyde back after we reduce our amide to an amine. Reaction 3 is called Benedict's reaction. Some aqueous solution of copper plus 2, which starts as a blue color, will react, and the copper gets reduced to a teal color. My apologies, that's the closest I could find to teal on this computer. Will react, and we're buffered to pH 2, so you're going to get a carboxylic acid, and its name will be L-N-propyl 3-aminotalonic acid. And what happens after that is we're supposed to make a lactam. How would one make a lactam? Well, you need an amine and a carboxylic acid derivative, or maybe just an amine and a carboxylic acid with the right catalyst combination. We're going to make a rather small lactam because there's our amine. And there is our carbonyl. They're going to connect. It's going to be a, let's see, there's the carbonyl. Alpha, beta. It's going to be a beta lactam. There are two ways to make our stereochemistry not ambiguous. You can go the old-fashioned way and do wedges and dashes for all your stereocenters. I retrofitted my talose over here with all the stereocenters done for you. Fisher made the bottom part easy because it didn't change from the original. And the rest is a little bit of hard work. You might want to just draw it without stereocenters and take the consequences. Save a little time. Alright, what's going on with lithium aluminum hydride and HCl? The only thing that can be reduced is the carbonyl. And miracles of ChemDraw, that would be the answer right there. Gets reduced down to a CH2. And I believe that's the end of that stream. Switching over here, we're going to convert our sugar to an alderic acid, carbon 2 having O-ethyl. Alderic acid is the one I misspoke about earlier, and it looks like this. It's this column here where both the top carbon and bottom carbon have become oxidized, both to carboxylic acids. Conjugate base is an alderate. So we're going to make this a carboxylic acid and the bottom one also. Now our job is to make a delta lactone here. How do we do that? We get our Greek on. There are two carboxylic acids, so two possible ways of doing our Greek alphabet. We got alpha for this carbon here, beta for this carbon here, gamma for this carbon here, and delta. There's an OH there. We can use that to make a lactone. Let's do so. How big will the ring be is the question. Well, the O here is going to be one atom in the ring. The other end of the ring will be where it connects to the carbonyl. I'm counting to 6, I think. 1 for the O, 2 for the carbon, 3, 4, 5, 6 for the carbonyl. Coming right up. Oh my, a lot went on there. I haven't finished this yet. I put the stereo centers on, which have changed because we oxidized the bottom carbon, raising its priority for the bottom two stereo centers. I also redrew a different, well, the same molecule with the alpha beta going from the other carbonyl. This is why we only have one delta lactone here. You can't make a delta lactone from this O to the carbonyl down here because it's not an alcohol. Later on we're going to do gamma lactones, and you've got two ways to go. You got this colorway. Gamma has an OH and gamma has an OH here. I'm just going to make sure the stereo centers are right and put the groups on here, and I'll be right back. These stereo centers are a lot of work, aren't they? And we've got that. And now it's off to our next mission of making the two gamma lactones from the same material. Let's do that. This last lactone turned out to be pretty tricky indeed, figuring out all the stereo centers, even when one of them is switching priorities from S to R, because a lactone has a higher priority than a former carboxylic acid. I am rather lenient on grading stereo centers on these lactones near the end, so please don't stress out. I hope you found this video on reactions of carbohydrates to be useful, and I look forward to our next video.